All right, we only have the one learning target to use relationships between arcs, chords, and diameters. Now, the book's going to remind us here of a couple things on page 701. It says, you learned that a chord is a segment with endpoints lying on a circle. All right, got it. If a chord is not a diameter, because it could be, right? The definition of a diameter is a chord that goes to the center of the circle. But if a chord is not a diameter, then its endpoints divide a circle into a major and a minor arc. Here's what they're talking about. If we look here at this figure at chord segment JH, it's awkward to call it chord JH, but the chord is called segment JH. It does divide the circle into two arcs. Arc JH, which is a minor arc, and arc JFH, which is a major arc. Okay? Now, to understand this next theorem, you need to understand the concept of a chord corresponding to a minor arc. Now, we've already matched arcs up with central angles, right? In the previous section, we would say that a central angle intercepts an arc, or an arc corresponds to a central angle. And the nice thing about that was that relationship between the central angle and the arc was that they had the same measure. Now, we could do that because they were both measured with degrees. We can't have quite the same relationship between an arc and a chord, because a chord can't be measured in degrees, it's a segment. Okay? But here's the way this works. In the same circle, or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So, this red arc, JH, and this black arc, FG, can be congruent if and only if their corresponding chords are congruent. So in other words, if we know those two arcs are congruent, we conclude that segment FG is congruent to segment JH. On the other hand, if we know that segment FG is congruent to segment JH, then we conclude that arc FG is congruent to arc JH. So, if the chords are congruent, that means the segments are. Wait, no, I said that wrong. If the chords are congruent, that means the arcs are. If the arcs are congruent, that means the chords are. Okay? One thing you can't get confused, though. They won't be measured the same way. Okay? The arcs are measured in degrees. The segments are measured in linear units. Centimeters, inches, whatever. Okay? So, if the length of that segment is 7 centimeters, that doesn't mean that that arc is 7 degrees. It doesn't mean that at all. All right? It doesn't mean that the length of the arc is 7 centimeters either. Okay? Let's see how this works out on page 705. 704. 704. All right, copy these down. These are part of your assignment. It starts off pretty easy. Number one's about as easy as it's going to get. They tell us to find the value of x. Now, we got a lot going on here. It's a real simple problem. You've looked at it. You probably already know the answer. At least you might. But let me walk through the logic here. Okay? Since segment RS is congruent to segment S, and then they didn't label that other point for some reason, I'll call it T. Since segment RS is congruent to segment ST, our conclusion is that arc RS is congruent to arc ST. So this arc is congruent to this one. Now, I know the measure of arc ST, and so do you. From the previous section, we know that when a central angle, an angle whose center is at the or whose vertex is at the center, when a central angle intercepts an arc, they have the same measure. So the measure of arc ST is 93 degrees. it's congruent to arc RS. So what's the measure of arc RS? 93. So what's X equal? 93. You follow the logic? Let's try number 2. Find the value of X again. I'll let you look at that for a minute. Think you got an idea of how to approach this one? All right, let me show you the way I'm thinking of it. Since I see a chord with a length of 4 and another chord with a length of 4, those two chords are congruent. Therefore, their corresponding arcs are congruent. So arc FG and arc GH are congruent. Since arc GH is called X, has a measure of X, well, so does FG. And then I think this, okay, if I start at one point on the circle and go all the way around, that's 360, correct? So 360 minus 220 is 140. So 140 has got to be the measure of that leftover arc. And that 140 gets divided into 2 equal parts, doesn't it? 70. Okay? Now, I could do this one that way because the measure was just X. But what if instead of X, the measure was 5X minus 13 in a parentheses with an exponent of 7 on it? You still think you could do all that in your head? The answer for me is no. All right? So let's make sure we can also do this algebraically. That arc has a measure of X. I know that all the way around the circle is 360, so I can do X plus 220 equals 360. So that's 2X plus 220 equals 360. And notice how the algebra works out the same way we did it without algebra when we did it in our heads. We subtract 220 to get 140, then we divide that by 2 to get 7. Okay? So when you're able to do them in your head, that's fine. I got no problem with that. Real, you're not always going to be able to. Okay? So case number 2. Number 3. We're still finding the value of X. Notice that the measure of arc AB is 127, and the measure of arc CD is 127. So those arcs are congruent. And if the arcs are congruent, so are the chords. And if those two segments are congruent, this turns into a problem that we could have worked the first week of school. If those two segments are congruent, doesn't that mean that 5X equals 3X plus 6? What does X equal? 3. Subtract 3X, divide by 2, X equals 6. Okay? Any questions? Okay. On page 702, we have two theorems together in a box. That usually means they're related in some way. So let's take a look at these. And before we do, right above it, it says if a line, segment, or ray divides an arc into two congruent arcs, then it bisects the arc. So when an arc gets cut into two equal halves, it's bisected. Just like a segment can get bisected and an angle can get bisected. And I copied the study tip on here. We call the line, ray, or segment that cuts the arc in half an arc bisector. Okay? Just like we have segment bisectors and angle bisectors, now we have arc bisectors. Now, before we read these two theorems, think about what we've talked about so far. So far, with our learning target, we have talked about relationships between arcs and their corresponding chords, haven't we? Now we're going to throw diameters in here. Okay? So, the first of these two theorems. If a diameter or radius of a circle, what do the diameter and the radius have in common? They both contain the what of the circle? The center. And a diameter contains a radius. but they both go through the center, don't they? So a segment that goes through the center, whether it's a diameter or a radius. So if a diameter or a radius of a circle is perpendicular to a chord, then two things happen. That diameter or radius bisects the chord, and it bisects the arc. So if we look at the figure here that goes with theorem 10.3, segment CD is perpendicular to chord XY. So according to this theorem, it bisects chord XY and it bisects arc XY. You with me? Okay. And then the next theorem says that the perpendicular bisector of a chord, well, look what we just did. Isn't segment CB a perpendicular bisector of that chord? Or if I lengthened it out and called it segment AB. So a perpendicular bisector of a chord is a diameter or a radius of the circle. Just depends on whether they drew the whole diameter or just the radius. So any segment that bisects a chord and is perpendicular to the chord has to either be a radius or a diameter, just depending upon how far you draw. Okay? You with me? Let's see how that works. So, number 4 and number 5 on page 704. In circle P, the length of JK is 10. So this red segment here is 10. And the measure of arc JLK is 134. So I'll make this red arc be 134. Find each measure. Well, first they ask us for the measure of arc JL. Hey, since this green radius is perpendicular to the chord, it bisects the chord and it bisects the arc. So wouldn't the measure of arc JL be half of 134? And what is half of 134? 67. Now, finding the length of PQ is a little more difficult. I'm going to make you work for this one. Okay? I will do this. The red segment that we started with, JK, had a length of 10. Well, since the green radius is perpendicular to it, JK got bisected. So doesn't that have to be 5 and that has to be 5? Now, they're asking us for the length of PQ, which I'll make blue here. Any ideas? Yeah. We're going to have to draw our own radius in. Now, let me caution you about a couple things that aren't going to be right. A common mistake is to think, well, that radius is 6, so this radius is 6, and that chord bisects it. The chord doesn't bisect the radius. The radius bisects the chord. So be careful with that. It's going to be really, really easy to put 3 and move on. And I'll virtually guarantee you on the quiz, somebody will do that. More than one somebody. And that's unfortunate, isn't it? Because that's not the way the theorem works. The chord doesn't bisect the radius bisects the chord. So, what Jordan said is right. Let's draw in a new radius. Because if the length of one radius is 6, the length of every radius is 6. A very common thing to do is to make a right triangle. You're going to do this 50 times in the rest of Unit 10, where you have to redraw or draw in a new radius to make a right triangle. Because look what happens. We already decided that length is 5. Can't we use the Pythagorean theorem now to find the missing length? And look, on this one, it's the Pythagorean theorem. If they'd given us an angle measure, maybe it's trigonometry we use instead. But we got a lot of tools with right triangles. This time it's Pythagorean theorem. So one leg squared plus the other leg squared equals the hypotenuse squared. So x squared plus 25 equals 36. So x squared equals 11, which means x equals 11. Now, that's the exact answer. But we're going to try to do a better job of actually following. So, 2 to the nearest 100. Use your calculator and tell me 3 point what? 32. So the length of PQ is 3.32 to the nearest 100. Everybody follow me on that one? Because once you've seen a couple of these, I think you'll be okay. But the first time you see one of those, you know, most of you may not think of drawing in a new radius. All right? Any questions? Okay. One more theorem. And it's on page 703. All right? And what this theorem is actually another way to determine whether or not two chords are congruent. We already learned that if two arcs are congruent, that their corresponding chords are congruent. We just learned that 10 minutes ago. Here's a new way to tell if two chords are congruent, and it's this. In the same circle, or in congruent circles, two chords are congruent if and only if they are equidistant from the center. So, segment FG and segment JH are congruent if and only if they're equidistant from the center. Now, remember how you measure the distance from a point to a line? It's with a perpendicular segment. So, the length of LX represents the distance that chord is away from the center. The length of LY represents the distance the other chord is from the center. If those two segments are congruent, then the chords are equidistant from the center, and if they're equidistant from the center, that means the chords are congruent. If the red segments are congruent, the chords are equidistant. If the chords are equidistant, they're congruent to each other. And vice versa. If the chords are congruent to each other, then they're equidistant. And if they're equidistant, then those two red segments are congruent. Everybody with me on that? All right, let's do number 6. This will be our last example from the assignment. It says in circle J, the length of GH is 9. So this red segment is 9. The length of KL is 4x plus 1. So the purple one is 4x plus 1. Find x. And you need to notice something here. What's the significance of those 5s? The same distance away. Those 5s are congruent to each other, so those two segments, those two chords, are equidistant from the center. And our theorem says if they're equidistant from the center, they're congruent. So 9 has to equal 4x plus 1. The length of the red one, 9, has to equal the length of the purple one, 4x plus 1. What's x equal? 2. Any questions? All right, so pause for a moment. Look at the learning target. Do you have any questions about the relationships between arcs, chords, and diameters? All right. Now, there's one other thing I want you to be able to do. This is not a learning target because it's not from a standard, but this is just kind of neat. If you do not have a compass, come get one from up front right now. All right, here's what we're going to do. The directions for this construction are on page 704. We're going to construct a circle through 3 non-collinear points. Okay? And remember with the construction, all you're allowed to use is a straight edge and a compass. So we're going to do it using a straight edge and a compass. Let's look at the steps the book gives us first, then I'll show you how it works, okay? So step 1 from the book is to draw 3 non-collinear points, A, B, and C, and then draw segment AB and segment BC. So that'll be easy. Step 2 is where the work begins. We have to construct the perpendicular bisector of each of those segments. And those perpendicular bisectors will intersect. If you draw them long enough, they will intersect. Okay? And then we're supposed to label the point where they intersect point D. And then, don't look at the drawing yet. Look at what it says under the last drawing. By Theorem 10.4, I've already forgot what it said. Here it is. The perpendicular bisector of a chord is the diameter of the circle. Oh, they just had us construct perpendicular bisectors of segments. So those perpendicular bisectors will contain diameters of the circle. And then think about it. Those two lines that contain diameters intersected at D. Well, where do diameters intersect? If two diameters intersect, they intersect at the center of the circle. So D is the center of the circle. Now we can draw the circle. So here we go. Put 3 points, A, B, and C, on your paper, and use your straight edge to construct segment AB and segment BC. I want to move point C a little bit. It's too close to horizontal. It messes up my little straight edge tool here. All right. Now what we want to do is construct the perpendicular bisector of each of those segments. So I think I'll do AB first. And we did a bunch of perpendicular bisectors way back when. Remember what you do? Put your compass point at one end, stretch the compass out so that it's more than halfway to the other end, then make an arc on each side of segment AB. Okay? Everybody got that? Leave your compass set the way you had it. And now, make arcs on each side, intersecting the arcs you already have, like so. You caught up to me? Now, where those two arcs cross, the intersection on each side, your perpendicular bisector goes through there. So use your straight edge. To make a perpendicular bisector. Now we do the exact same thing to bisect segment BC. Put your compass point at one end point. Stretch your pencil out so that it's more than halfway to the other end. And then make an arc on each side of segment BC. Leave that same compass setting and then intersect the arcs that you just made. Use your straight edge to go through the intersection on both sides of segment BC, and you've constructed the perpendicular bisector of segment BC. You with me? They got to cross somewhere. And now the real fun begins. Because now the point where your two perpendicular bisectors intersect, that's the center of the circle. So put your compass point where your two perpendicular bisectors intersect. And then adjust the setting so that the pencil is on either point A, point B, or point C. It doesn't matter. See how I've got mine? Draw your circle. Isn't that neat? You just constructed a circle through 3 non-collinear points. And the thing I like about this construction is, doesn't that seem kind of impossible? Before you do it, you think, well, I can't make a circle go through those 3 points. Yeah, you can. And you just did. And it's all because perpendicular bisectors are diameters. Diameters intersect at the center. Any questions on the construction? On page 704 then, do 1 through 23, 31 through 33, and 40 through 46.